All right, so today we have Daniel Baldwin who will tell us how to classify special holonomy Kummer constructions. Take it away.
Okay. Yeah, so thank you, Julius. Thank you for the invitation to the meeting. It's nice to be here. So yeah, I'm Daniel, and I'll do as Julius just said. Um, so, as the title suggests, this talk will discuss results from efforts to classify special holonomy Kummer orbifolds. So, special holonomy here could mean Calabi-Yau or hyperKähler, for example, and Kummer orbifold is synonymous with toroidal orbifold in this talk. And all this work is in collaboration with Bobby Acharya. So the broad outline, I'll start by talking about compact special holonomy spaces in general, and then briefly justify why they're interesting physically. Then I'll talk about these toroidal orbifolds, these orbifolds of Kummer type, what they are, and then I'll talk about how to go about classifying them. And then I'll discuss some results in this direction for the hyperKähler case in 8 dimensions, and then some preliminary results for the G2 case. And then I'll discuss some directions for the future as well. So string theory and M theory predict extra dimensions of spacetime, as is well known, and we're often interested in compactifying these theories to obtain some lower dimensional effective theories. And the simplest way we can do this is to just take our 10 or 11 dimensional spacetime to be a Riemannian product of Minkowski space with some compact manifold or orbifold X. And then we can perform some Kaluza-Klein style analysis on the higher dimensional fields to obtain some effective theory in the Minkowski space. And then if we require that our spacetime satisfies the Einstein equations, the vacuum Einstein equations, with a couple of other assumptions, this forces our compact space X to be Ricci-flat. So at present, all known examples of compact Ricci-flat simply connected manifolds have special holonomy, and in particular, they're either Calabi-Yau, hyperKähler, G2, or spin 7 manifolds. And conversely, all compact manifolds with these holonomy groups are Ricci-flat. And interestingly, these are also precisely the compact irreducible Riemannian manifolds, which preserve some fraction of supersymmetry upon compactification of string theory or M theory. And that's related to the fact that they have some covariantly constant spinors. So another interesting fact is that string theory and M theory make perfect sense when this compact space X has certain singularities. And in fact, this typically gives rise to the most interesting physics. So it's often the case that particular singularities inside special holonomy spaces support interesting interacting quantum field theories. So this is the idea behind geometric engineering. And so some well-known examples are in G2 compactifications of M theory. So these are cases where we take our 11-dimensional spacetime to be 4D Minkowski times a compact 7 orbifold with holonomy group G2. Non-abelian gauge symmetries in the effective theory in Minkowski space are supported at codimension 4 ADE singularities, and chiral fermions are supported at particular codimension 7 conical singularities in the G2 orbifold X. Another example is one can engineer 5-dimensional superconformal field theories by compactifying M theory on Calabi-Yau threefolds with certain singularities, which is also well known. And then there are many other examples. So we understand the physical interpretation of only particular kinds of singularities that can occur inside special holonomy spaces. But the array of possible singularities that could occur is vast and largely unexplored in general. So it'd be good to have a more complete understanding of the physics of, say, M theory on some given singularity. So, for example, what is the physics of M theory on some given codimension 7 orbifold singularity inside a G2 orbifold, or the physics of M theory on some given symplectic singularity. So for example, C4 quotiented by this group. So in summary, compact singular special holonomy spaces are interesting physically. And so we'd like to have examples of them. And one of the simplest ways to obtain compact special holonomy orbifolds is to quotient a torus. So Tn, this torus here is just Rn quotiented by some lattice lambda. We take that torus and quotient it by a finite group of isometries H, which preserves some special structure. So for example, a Calabi-Yau structure, or a hyperKähler structure, or a G2 or spin 7 structure. And the resulting space is then known as a toroidal or Kummer orbifold. Such orbifolds with sufficiently tame singular sets, and what it means to be tame will be specific to the holonomy group that we're considering. But such orbifolds with sufficiently tame singular sets could give rise to new compact special holonomy manifolds. And this is using methods pioneered by Dominic Joyce, who constructed the first compact G2 manifolds through these methods. A complete and thorough classification of all Kummer orbifolds hasn't been attempted for real dimensions greater than 6. So for 7 and above, the number of Kummer orbifolds isn't known. And you can see work by Fisher and collaborators from 2012 for the Calabi-Yau examples. So they classified all 6-dimensional Calabi-Yau toroidal orbifolds. And we're continuing this work further. So for the rest of the talk, I'll discuss Kummer orbifolds in general, and then I'll discuss results that we've obtained in the hyperKähler case before moving on to some preliminary results in the G2 case, and then some projections for the future. And as I mentioned, this is all in collaboration with Acharya. So I'll say a bit about Kummer orbifolds in general. So a general philosophy for, well, a general recipe for creating Kummer orbifolds is the following. So we choose some n-dimensional lattice, lambda, and then we can create a torus simply by quotienting Rn by that lattice. And then if we take some finite group H, which preserves that lattice, so in other words, it sits in the automorphism group of that lattice, we can quotient Tn by that group, and we'll obtain, generically, we'll obtain some singular space, some orbifold Tn mod H. Now, generally, this group H, this finite group of isometries, can act by translations and rotations simultaneously. And so it's actually cleaner to describe this group in terms of space groups. So I'll just define what they are. So given some H in the automorphism group, given some subgroup of the automorphism group of a lattice, lambda, we can define some H hat, which sits inside the Euclidean group, ON semidirect Rn, such that under the map, which forgets translations, so this pi just projects onto the rotation factor. Under this projection, the group H hat is isomorphic to H, and the kernel of this map is isomorphic to the lattice lambda. So this just means that the group H hat contains the lattice lambda as a normal subgroup. So we can then more generally think of our orbifolds as being quotients of Rn by what's known as a space group H hat. So because H hat contains the lattice as a normal subgroup, we get, by quotienting by it, we get the torus, and then we act on it by the finite group of isometries kind of in one step. So in the language of crystallography, this is where this comes from, H hat is known as a space group, and H, its rotational part, is known as a point group. So I'll use that language throughout, space group and point group. And generally, H hat is not isomorphic to the semidirect product of its rotational part and the lattice. So we'll see that in an example in the next slide. But it contains the lattice as a normal subgroup, but it's not generally a semidirect product of these groups. And we have a notion of equivalence between space groups. So we call two space groups affinely equivalent if they're conjugate inside this Euclidean group, ON semidirect Rn. So that and two affinely equivalent space groups will be considered the same. Okay. So yeah, by way of example, we can look at 2 dimensions. So in 2 dimensions, there are 17 affine equivalence classes of space groups, and these are known as the wallpaper groups, and they've been known for a very long time. So we can look at an example here. We take R2 with coordinates x and y, and then we consider the following generators. So we have G1, G2, T1, and T2. G1 rotates x and y, well, it acts as -1 on y, and also translates at the same time. G2 only rotates x and y, and then T1 and T2 only translate. And the collection of these guys together, they generate a space group, which I'll call H hat. And the point group, so the projection onto the rotational part, is isomorphic to Z2 squared. So that's just the group generated by these two order 2 matrices. And then the generators T1 and T2 generate the square lattice inside R2. And this example here isn't isomorphic to the semidirect product of its point group and its translation lattice. And the reason for that is that this element G1 translates by a vector which doesn't live in the lattice, in this square lattice. So you can't apply T1 and T2 to kill that. So H hat contains the lattice as a normal subgroup, but it doesn't contain its point group as a subgroup. So that's one example of a space group. And this clearly acts with fixed points. And so if we quotient R2 by this space group, we'll get some two-dimensional toroidal orbifold with some singularities. Now we can alter G1 slightly just by changing the translation that it acts by. So it still acts by -1 on y, but now it translates in the x direction as well. And this new action acts freely on R2 because it translates in this action which isn't being rotated. And if we replace G1 by G1 prime, we'll get a new group H hat prime. So this is another space group, and this isn't affinely equivalent to H hat. So there's no element of the Euclidean group which can conjugate one into the other. But they do have isomorphic point groups. So both their point groups are isomorphic to Z2 squared. Okay, so that was 2 examples of space groups. And now I'll just give an example of a special holonomy orbifold and how one can desingularize a special holonomy orbifold to obtain a special holonomy manifold. So the kind of prototypical example is the Kummer construction of a K3 surface. And this is the origin of the name Kummer used throughout this talk. So if we take some four-dimensional torus, just R4 quotiented by the square lattice, we can define some complex coordinates on it, which have period 1. And we can define a hyperKähler structure on T4 in these coordinates, given by equation 2 here. Then we can consider the group which acts as -1 on these coordinates. And this action fixes 16 points on the torus. And these are precisely the points where xi is either 0 or a half. And this group action also preserves the hyperKähler structure. So if we quotient T4 by this Z2 action, we obtain a hyperKähler orbifold. And the singular set of this orbifold is 16 A1 singularities. So 16 points modeled on C2 mod Z2. Each of these singularities admits a symplectic resolution given by the Iguchi-Hansen space. So this is just the blow-up of this A1 singularity. And one can remove a neighborhood of each of these 16 singular points and glue in this smooth space. And then, so topologically, then we have a manifold and it's smooth. And you can prove that there is a hyperKähler metric on this resulting space. So the way this goes is the following. So the resolution of these singularities is a symplectic resolution. And so what that means is at the end, you're left with a compact Kähler manifold with a globally defined holomorphic symplectic form. And then the Calabi-Yau theorem guarantees the existence of some Ricci-flat metric, which in this case is a hyperKähler metric. You don't get the metric explicitly from this theorem, but you can approximate it by the flat hyperKähler metric almost everywhere. So the hyperKähler metric defined in equation 2. And then close to these 16 gluing regions, you can approximate the metric by the Iguchi-Hansen metric. So the hyperKähler metric that you have on the resolution of the singularities. And then you can use geometric analysis to prove that you can perturb this approximately hyperKähler metric to a genuinely hyperKähler one, to a genuinely Ricci-flat metric. So in the crystallography language that I introduced before, the space group of the previous example is just the semi-direct product of the point group Z2 and the square lattice. So here the space group actually is a semi-direct product because the point group, the group action isn't acting by translations at the same time that it's rotating. And the orbifold is just R form of this space group. And there are actually 10 different affine equivalence classes of space groups in 4 dimensions, such that that give rise to Kummer orbifolds that can be desingularized to a K3 surface. And you can compare this with, so the total number of space groups in 4 dimensions is over 4,700, and only 10 of these give rise to K3 surfaces. And this was found by Fujiki in 1988. And the point groups of these space groups are given in this list here in equation 3. So Z2 is the example we just discussed, but then there's also 3 other cyclic cases. There's 2 binary dihedral cases, one of which has 3 affine equivalence classes of space groups. And then there's the binary tetrahedral group case. Okay, so that's an example of a special holonomy Kummer orbifold. So just to summarize all that I just said, every Kummer orbifold is of the form Rn mod h hat, where h hat is a space group. So this is a subgroup of the Euclidean group that contains an n-dimensional lattice as a normal subgroup. And the point group associated to a space group is just the natural projection onto On, just the rotational part. So Kummer orbifolds are one-to-one with affine equivalence classes of space groups. So if we want to go about classifying Kummer orbifolds, this is exactly the same problem as classifying space groups up to affine equivalence, which is a classic problem. So it's known that in each dimension, n, there are only a finite number of affine equivalence classes of space groups. This was shown by Bieberbach. And in principle, it's known that you can compute all space groups in a given dimension algorithmically. And this is due to Zassenhaus in 1948. But this is computationally very difficult for high dimensions. So yeah, the space group problem can be just stated: find a representative of each affine equivalence class of space groups in a given dimension, n. So Zassenhaus reworded this problem slightly in a way that lends itself more to being applied on a computer. So you can reformulate this space group problem in the following way. So you first have to find the set Gn, which is the set of representatives of each conjugacy class of finite subgroups of GLNZ. This is your set of possible point groups. And then for each G in Gn, you want to find all space groups whose point group is that G, up to affine equivalence. And this can be implemented algorithmically. Oops. Oh dear. So as I mentioned, this is doable in principle, but computationally difficult. So in this table, I just summarize what's known up to dimension 6. So in dimension 2, we have these 17 affine equivalence classes of space groups, which are known as the wallpaper groups that I mentioned before. And we go all the way up to dimension 6. We have, so in this second row is the number of possible point groups. So there's 85,000 possible point groups and over nearly 29 million possible space groups. with those point groups. And then for dimension 7, as far as I know, the answer isn't known, and for higher, it's not known either. So it's been estimated by this work from 2002, roughly, that in 7D there'll be around 17 billion space groups, and in 8D around 35 trillion, and then it continues to grow with this factor 2 to the 2 to the n. So it gets difficult very quickly. But if we try to find space groups that preserve some special holonomy structure, then the problem becomes tractable, because we're placing quite strong restrictions on this set Gn of possible point groups. We're only keeping those that preserve a special holonomy structure. So for example, this work that I mentioned by Fisher and Ratz and collaborators from 2012, they classified all Calabi-Yau Kummer orbifolds in dimension 6, and they found 520 out of the 29 million possible 6D space groups. So we're just continuing this analysis for other special holonomy groups in higher dimensions. Okay, so our methodology is the following. So we start by taking a maximal finite subgroup G of GLNZ. These are all characterized as automorphism groups of some lattice, thanks to work of Conway and Sloan. So I'll say a bit more about that in a second. So we take some maximal finite subgroup of GLNZ, and then in step 2, we find all of its subgroups which preserve the special structure that we're interested in. So for example, a G2 structure in 7 dimensions. And then we repeat this for all the maximal finite subgroups.
What does maximal mean?
There's no finite, there's no other finite subgroup which contains it as a subgroup. And then in step 3, we collect all of these in a list, and then we reduce them up to conjugacy in GLNZ. And this then gives us a list which I've called H prime, which is our list of possible point groups. So steps 1 to 3 just give us our list of possible point groups which preserve the special structure that we're interested in. And then the final step, step 4, is just to take each of the point groups in this list and find all of the space groups that have that point group. And this gives us our list of possible special holonomy Kummer orbifolds. And yeah, so we made heavy use of the discrete algebra programming language GAP for this work. And yeah, and so we've done this process for the 8-dimensional hyperKähler case, but we restricted the lattice to the E8 lattice, which in hindsight was unnecessarily restrictive. So there's more to do here, but we have results for that case, and then we also have some preliminary results for the G2 case for all 7D lattices. So I mentioned that Conway and Sloan classified all the maximal finite subgroups of GLNZ as automorphism groups of some lattice. So this is just a snippet of one of the tables from their paper. So each row in the table here is a maximal finite subgroup of GLNZ, which is irreducible, so it can't be block diagonalized. So here the 7D guys, so D7 here is one of the lattices. This is just saying the automorphism group of the D7 lattice is a maximal irreducible finite subgroup of GL7Z. And so there's however many there are, 7 of these guys. So for the G2 case, we took all of these, and then we also took the 6+1 lattices and the 5+2 and the 4+3, and took all their subgroups, kept the ones that preserved the G2 structure, and then found all their space groups. For the hyperKähler case, we did this just for the E8 lattice, but as you can see, there's many more possibilities, and this isn't even the full table. So there's.
Could I?
Of course.
Could I ask a naive question? It's about this maximality condition. What about things which are not irreducible, like, and for instance, product of cyclic factors, which presumably don't have a maximal I mean, I can.
Yeah, so well, yeah, I'm not sure if I understand the question, but so we're taking these maximal subgroups and then taking all of their subgroups to get our
Right.
full list.
So is it just that, for instance, if I try to take a group like, in GL, I don't know, 4Z or something like this, like a product of two cyclic groups with very large orders, you're saying, well, there's just not going, there's something that tells me that there's not going to be any lattice that's invariant under it. I mean, I expect it's only going to be true if the orders of the cyclic groups are like, 2, 3, 4, and 6 or something like this. But I'm just trying to understand what told you that you only needed to find these, you only needed to look among these maximal finite groups.
Well, this was, yeah. So the space group problem as formulated by Zassenhaus says we need a set of representatives of every conjugacy class of finite subgroups of GLNZ. And so one way to get all the finite subgroups of GLNZ up to conjugacy is to start with the maximal guys, take all of their subgroups, and then reduce that list up to conjugacy in GLNZ.
Well, I'm sorry.
Maybe I'm
in
missing.
GLNZ, a very simple subgroup is I see. Okay. Oh, I think I understand. Sorry. I think I was just being confused. Okay.
No problem. Thank you for the question. Okay, so yes, so using Conway and Sloan, we can get all these guys. Okay, so that's Kummer orbifolds kind of in general. So now I'll focus on the results we got for the hyperKähler case, and then I'll say about the G2 case and then some future directions. So for the hyperKähler Kummer orbifolds, our original inspiration wasn't to classify all hyperKähler Kummer orbifolds. It was actually to try and find a new example of a compact hyperKähler manifold. And the way we wanted to do this was to search through some large class of hyperKähler orbifolds and try and find some example that had a sufficiently nice singular set such that we could desingularize it and obtain a new compact hyperKähler manifold. So I'll just state the definition of a compact hyperKähler manifold. So these are, sorry.
When you look for those singularities and you try to make it smooth, is this a simple process to take singularity and smooth it out?
Yeah, so, well, it could be quite subtle, but at least a necessary condition is that all of the singularities in the singular set admit a symplectic resolution.
Do you know it for sure that they all admit symplectic resolution?
No, so, well, we'll actually see that we didn't find a new example of a compact hyperKähler manifold. So it's really hard to find examples such that all the singularities admit a symplectic resolution.
Yeah, this has been a challenge for several decades now, right? To find spaces which are not the ones which are already known.
Yeah. Yeah, it's a really, a very restrictive condition.
Yeah. Okay, thank you.
No problem. Thank you. So so a compact hyperKähler manifold is some 4n-dimensional compact Riemannian manifold whose holonomy group is SPn. And equivalently, they can be viewed as compact Kähler manifolds that are simply connected and admit some holomorphic 2 form that's closed and non-degenerate on all of X. And then a hyperKähler orbifold just has this structure defined on its smooth part. And a more hands-on way to view hyperkähler manifolds and orbifolds is that they admit some triple of two forms, omega I, j, and k, which at each point take this kind of standard form. And the metric is Kähler with respect to each of these and so on. So there are very, very few examples of compact hyperkähler manifolds known in each dimension. So this was the kind of motivating problem. So in a given dimension 4n, there are essentially just two examples, which are the first two bullet points here. The Hilbert scheme of n points on a K3 surface is one of the examples. And the generalized Kummer variety is another example. So these occur in every dimension that's a multiple of 4, and that's basically all you get. Except there are two exceptional examples in real dimension 12 and real dimension 20, which were found by O'Grady. But this was, a long time ago, so there have been no new examples found for nearly 30 years. So our plan was to try and classify all hyperkähler Kummer orbifolds, which were obtained as quotients of the maximal torus of E8. And the reason for this choice is that this torus has a very big symmetry group given by the Wahl group of E8. This has like order 700 million. And therefore, we expected it to provide many candidate orbifolds and kind of increase our chances of finding something that could be desingularized to a compact, smooth hyperkähler manifold. So in order to do this, we needed to classify all subgroups of the Wahl group of E8, which preserve a hyperkähler structure. So in space group language, the orbifolds from point 1 will be of the form R8 mod H hat, where the point group preserves the E8 lattice. So it's a subgroup of the Wahl group of E8. This point group then must preserve a hyperkähler structure. If we want these orbifolds to be hyperkähler orbifolds, this point group must preserve a hyperkähler structure. And this is equivalent to it being a subgroup of sp2 acting in its 8-dimensional holonomy representation. So we can do this, we get a list of possible point groups. And then in step 3, we want to take each of these point groups and classify all of their space groups, and then quotient the maximal torus of E8 by these space groups, or quotient R8 by these space groups, and study their singular sets. And then if we can find some example such that all of the singularities in this singular set admit a symplectic resolution, then we might have a candidate for a new compact hyperkähler manifold. So I'll just go into some more detail in steps, on steps 2 and 3. So step 2 first, trying to classify all the subgroups of the Wahl group of E8 that preserve a hyperkähler structure. So this makes use of the phenomenon of triality in 8 dimensions. So we start by identifying R8 with the octonions, and then the E8 lattice sitting inside R8 can be viewed as a discrete subring of the octonions, which are often called the integral octonions. So I'll just call that D, but it's isomorphic to the E8 lattice, but also a subring of the octonions. Then spin 8 is the isotopy group of the octonions, and so it can be defined in the following way as a subgroup of SO8 cubed. So it's the set of triples G1, G2, G3, where each of these are elements of SO8 that satisfy this condition here. So we take three octonions, X, Y, and Z. We take their product, and then we take the real part on the right-hand side. And on the left-hand side, we act on X, Y, and Z by G1, G2, and G3. So this is just like rotating 8D vectors in R8. Then we multiply them using the fact that they're octonions, and then we take their real part. And if the left-hand side agrees with the right-hand side, this triple is an element of spin 8. And all of spin 8 can be obtained in this way. And from this description, we get 3 natural projection maps onto the SO8 factors, and these are all the double covering maps from spin 8 into SO8. So we get 3 double covering maps, pi1, pi2, and pi3. And now the classification hinges on the following facts. So if you take some 5-dimensional subspace W inside R8, or inside the octonions as we're viewing it here, we can think of that as sitting in the R8, which is acted on by this first factor, this first SO8 here. And then we define SOW to be the group which acts trivially on the orthogonal 3D subspace. Then we can lift that SOW into spin 8 by taking the pre-image under pi1. So we start with this SOW, we lift it to what I'll define as spin W, and this is some subgroup of spin 8 now. Now, since minus the identity in SO8 doesn't live in SOW, otherwise it wouldn't act trivially on the 3D orthogonal subspace, the pre-image of SOW under pi1, so this spin W, doesn't contain these two elements, -1, 1, -1, and -1, -1, 1. And the upshot of that is, when you project spin W down into the other two factors using pi2 and pi3, the kernel is trivial. So this map is 1-to-1, and these projections of spin W are still non-trivial double covers isomorphic to spin 5, which is itself isomorphic to sp2. And they also act irreducibly on R8 now, instead of reducibly. So we started with this SOW in the first factor acting reducibly on R8. We took its pre-image under pi1 and then projected it onto one of the other two factors, and we obtained some group isomorphic to sp2 acting irreducibly on R8. And this representation is precisely the hyperKähler holonomy representation of sp2. So the point of this is, if we take a subgroup gamma of this SOW in the first factor, and we take its pre-image, so we take some finite subgroup, say, then we take its pre-image in spin 8 and then project it into the one of the other two factors using pi2 or pi3. The group that we obtain is a subgroup of sp2, and it acts irreducibly on R8. In other words, it preserves a hyperKähler structure. So yeah, if there's no questions, I'll carry on. So we also want these subgroups to preserve a lattice. So to preserve the E8 lattice in our case. So we take gamma to be a subgroup of the Wahl group of E8, but with determinant 1 because we're inside SO8. That acts as the identity on some 3D subspace. And you can show that all of these groups gamma will just be the automorphism groups of 5D sublattices of the E8 lattice. So you can classify all of those. Each of these gammas will be generated then by pairs of Wahl reflections. So these are just reflections through lattice vectors. And using the definition of spin 8 that I gave on the previous slide, you can show that the pre-image of a pair of Wahl reflections in spin 8 is this set of two elements. So you have the pair of Wahl reflections, and then you have a pair of left multiplications by octonions and a pair of right multiplications by octonions. So then when you project onto the second or third factor, so for example onto the second factor, you get this group which is, instead of being generated by pairs of Wahl reflections, it's generated by pairs of left multiplications by these lattice vectors, which are viewed as octonions. So in the end, we have this group, which preserves a hyperKähler structure because it's a subgroup of sp2 acting in the correct representation. And it also preserves the E8 lattice, viewed as this subring D, precisely because the E8 lattice is closed under multiplication. So it's a discrete subring of the octonions. So it's closed under left multiplication by its own elements. So yeah, so the upshot is we can obtain all the groups that preserve an E8 lattice and a hyperKähler structure in 8 dimensions through this process. Okay, so step 3 from a few slides ago stated that we need to look at the singular sets of all the hyperKähler orbifolds that we obtain and try to find an example that could be desingularized to a smooth hyperKähler manifold. And a necessary condition for this to be true is that all the singularities in the singular set admit a symplectic resolution. So I'll just define what symplectic singularities are and what a symplectic resolution is, and then say what's known about them. So if you take some finite subgroup of SPN G and a vector space V, which is a symplectic representation of this group, then V mod G is a symplectic singularity, and it admits a two form that's closed and non-degenerate on all of its smooth part. So that's the definition of a symplectic singularity. And oh dear, sorry. And a desingularization of this singularity is called a symplectic resolution if the pullback of the two form on the singularity is also closed and non-degenerate on all of the resolution V mod G tilde. So the current list of singularities which are known to admit a symplectic resolution is the following. So I won't go into detail in these, but the point is the list is very small. So in each dimension 4n, there are these first two bullet points. So the V mod G can always admits a symplectic resolution in these cases. And then in 8 dimensions, there are the last two bullet points as well. So you have these two exceptional guys. So the list of possibilities is very small. So I'll just to say that. This isn't a complete classification of all singularities that admit symplectic resolutions. As far as I can tell, there's still 45 open cases left to consider. And this work is due to several people, but more recently I've seen work of Bellamy and Shedler talking about this. And they stated in one of their papers that they expect this list here to be complete. So they don't expect there to be other examples of singularities which admit symplectic resolutions.
So what are these 45 cases? What are these 45 cases? They're like in other Weyl groups or
they're just other finite subgroups of SPN. I can't remember
okay
what they all are,
but so they're not symplectic. They don't have a symplectic resolution.
They may or may not have a symplectic
resolution. But it's believed not to.
It's expected that they don't. Yeah.
Okay.
Do you know if it's complex reflection or symplectic reflection?
Could you say that again? Sorry.
Do you know if the orbifold groups are complex reflection or symplectic reflection?
I can't remember. Sorry. Yeah, I'm not sure.
Okay.
Okay. So so we did all of this and we presented the results in a paper earlier this year on the archive. So it turns out to be very hard to find examples with appropriate singular sets, precisely because the list of symplectic resolutions is so small. And so it was more efficient to rule out examples just by finding any singularity which didn't admit a symplectic resolution in the singular set. And in the end, we found no new compact hyperKähler manifolds through this method. So it was kind of a negative result. The only examples we found where all the singularities did admit a symplectic resolution gave rise to compact hyperKähler manifolds that were already known in the literature that I mentioned before. But we did find hundreds of new compact hyperKähler orbifolds. And this project inspired the broader goal that I've been discussing of classifying all compact special holonomy Kummer orbifolds. So in particular, there's still many more hyperKähler Kummer Orbifolds to classify in dimension 8. We only looked at those associated to the maximal torus of E8. So this is far from over. So we might still yet find a new compact hyperKähler manifold, but it's definitely a hard problem. Okay, so moving on from the hyperKähler case, I'll say something about the G2 case now. So following from that, we wanted to try and classify all G2 Kummer orbifolds next. So I'll just define what a G2 manifold and orbifold is. So it's a 7-dimensional Riemannian manifold whose holonomy group is contained in the exceptional Lie group G2. And equivalently, a more hands-on definition is that this 7 manifold admits a smooth 3-form phi that at every point looks like the standard G2 structure on R7. So this is just a particular 3-form, which I've written out here. And then we also require that phi is closed and co-closed. So phi defines a metric, and so you can define some Hodge star, and then you want phi to be harmonic with respect to that metric. And then M is a G2 manifold. And again, G2 orbifolds just have this structure defined on their smooth part. These spaces are interesting, so they're vital ingredients in M-theory compactifications. And this is because they're Ricci-flat and they have exactly one covariantly constant spinor. So what this means is if one wants 4-dimensional n equals 1 supersymmetric theories by considering M-theory compactifications on spacetimes of this form, then G2 manifolds are the only possible candidates for these compact spaces X. G2 manifolds or orbifolds. Okay, so to classify all G2 Kummer orbifolds, we followed our general strategy. So to start, we want to find all possible 7D point groups. And so we, again, used this work of Conway and Sloan that I mentioned before to get all of the possibilities. Then in step 2, we want to keep only those groups which preserve a G2 structure and then reduce the list up to conjugacy. So we can, I don't go into detail, but we can use the same method that I mentioned before using the triality map. So we can take a given point group, map it to its spinor representation using the triality map from before. And then we keep only those groups that preserve one direction in their spinor representation. And this uses the fact that G2 is the subgroup of spin 7 that preserves precisely one direction in the 8-dimensional spinor representation. So spin 7 is the subgroup of spin 8 which preserves a direction, and G2 is the subgroup of spin 7 that preserves another direction. So then this gives us our list of possible point groups preserving a G2 structure. And then in step 3, we take each of these and we classify all of their space groups. And so this just amounts to plugging them into an algorithm that we've written in GAP following the work of Zassenhaus. And this generates all of our space groups. And then eventually we would want to analyze all their singular sets and other things. So the results of this process that we have so far, so we have all the space groups. So there are over 35,000 G2 Kummer orbifolds. And it's interesting to compare this to Dominic Joyce's original work, where he considered roughly 20 orbifolds. And from these, he constructed the first examples of compact G2 manifolds using his generalized Kummer construction. So we have 35,000, over 35,000. We're yet to study all of their singular sets. This takes a long time, but we already know that many of these will satisfy the conditions of Joyce's theorems that he used to construct these compact G2 manifolds. And therefore they will admit desingularizations and will give many new examples of compact G2 manifolds. So that's interesting for M theorists and also interesting to mathematicians. There are many examples which we don't know how to resolve yet with the current theorems, but these still have interesting configurations of singularities in various dimensions. So I'll just flash this. So this is like an example of the output of our code, which analyzes the singular set of a given Kummer orbifold. So like the first block here is the singular set of one particular orbifold. So what this means is so like this first row means it has a component of its singular set, which is codimension 7, and the singularity is of the form R7 mod this order 24 group. So it has this gap ID 2412. And there's 8 of these fixed points, and then there's various other fixed points of various codimensions. So we get quite intricate configurations of singularities. And the physics of these various singularities is yet to be explored. So there's lots to do there. We also have several hundred.
How is this done? If you have some singularities, how do you figure out the physics? Or like what can you say about the physics?
Yeah, well, I guess largely we don't know because it's not known, but like, so we know that codimension 4 singularities, AD singularities, give rise to non-abelian gauge symmetries, and then it's known for some particular conical codimension 7 singularities that you get chiral fermions. So if you have configurations of both of these, then you get chiral fermions charged in the non-abelian gauge groups. Codimension 6 singularities should give rise to 5D SCFTs. Yeah, so there's. I guess the answer is I don't know. We'd have to.
Okay.
It needs to be explored.
All right.
Yeah, and then finally, we also have several hundred examples of flat G2 manifolds. This is where the quotient is free, so this space group acts freely on R7. And some of these have very low Betti numbers, and these are interesting physically as they should give rise to exact 4D quantum gravity theories from M-theory compactification. Okay, so that's a summary of all the results we have so far for this. So in the future, we would like to continue this classification for other special holonomy groups and other dimensions. So there's loads more to do. We'd like to create new examples of compact special holonomy manifolds. The most interesting possibilities that we expect to find in the near future are new compact hyperKähler manifolds and new compact G2 manifolds. And we'd also like to study the physical interpretation of these various complicated configurations of singularities that will arise as a result of this project. So that's everything. So thank you everyone for your attention.
All right, let's thank Daniel. Do we have questions? All right, so we had a few questions during, so I'd say let's thank Daniel again.
Yeah.
And we can go off the record.